So next we have D for diuretics. And how diuretics work is essentially aim at the kidneys, affect the kidneys. It increases urine volume by an action within the tubule. So it wants to release more urine, or more substances in the urine. And it targets the nephrons, the functional unit of the kidneys, because this is where everything passes through. So here's the head of the nephron, the proximal convoluted tubules, the loop of Henle, the distal convoluted tubules, finally going out the collecting ducts into the urethra. So it goes this way. This way. Now there are many types of diuretics which affect many places in the tubules of the nephron, but we'll talk about two. One that affects the loop of Henle, called the loop diuretics. An example of loop diuretics is furosemide. And another type of diuretics we're going to talk about is the one that affects the end of the ascending loop of Henle, known as thiazides. Now they're very similar, they work very similar within the tubules, they affect within the tubules, and we'll talk about the thiazides. So we'll zoom into this section here, in between the blood vessels and the inside of the tubule. So we'll zoom in, and we'll rotate it 90 degrees for simplicity. So basically, on the very top is we find the lumen. On the top here, we find the lumen, the inside of the tubule. So this is the inside of the tubule. And it contains sodium and chlorine ions. But it contains other molecules, but we just want to aim at these specific ones because this is what affects how the diuretics work. And surrounding the lumen are epithelium cells, the one that absorbs any molecules that needs absorbing. And finally, we have the blood vessels where it gets collected. So, and here in between the lumen and the epithelium cells, we have a transporter, a receptor called a co-transporter. So it transports two molecules at once, two different molecules. So here we have a sodium and chlorine co-transporter, which then gets absorbed in the epithelial cells and then gets excreted to the blood, basically increasing blood pressure. So essentially, what the thiazide diuretics do is that they block the co-transporter. It blocks the chlorine molecule. So if the chlorine is blocked, the chlorine doesn't get absorbed, but that means the sodium doesn't get absorbed, and so none of them get absorbed, and so the blood pressure drops. And so what is the difference between thiazides and loop diuretics is that thiazides has a longer effect, and it promotes calcium retention, so it absorbs calcium from the tubule. Loop diuretics, on the other hand, has a short duration, and it enhances the urine calcium loss. Finally, lastly, we have E for endothelium antagonists. And so we'll just look at how it works normally. So here we have the lumen of a blood vessel surrounded by epithelial cells, vascular epithelium cells. Now these vascular epithelium cells, they secrete a peptide called endothelin, mostly known as endothelin 1, and I'll denote it as ET. So endothelin, and then surrounding this, the blood vessels, the smooth muscle, which is required for contraction. It's normal in every blood vessel. And so these smooth muscles, they have receptors for endothelin. They have two receptor types. They have endothelin 1 receptor, and endothelin B receptor. And these two receptors causes vasoconstriction, so increase in blood pressure. There are also endothelin receptors, endothelin B receptors, found on the vascular endothelium cells. And what they do is that when it binds, it secretes nitric oxide. So when endothelin binds to these receptors on the vascular endothelium, it secretes nitric oxide, which then binds to receptors found on the smooth muscle, a different receptor found on the smooth muscle, which causes vasodilation through a cyclic GMP mechanism. So endothelin can bind to these receptors here, causing vasoconstriction. It can also bind to the vascular endothelium cells, again, different, causing the endovascular endothelium to secrete another substance, nitric oxide, which then can bind to the smooth muscles through a different receptor, cyclic GMP mechanism, G protein, causing vasodilation. And this is interesting because endothelium actually causes a transient vasodilation due to the nitric oxide, and then it causes a prolonged vasoconstriction due to the normal receptors. And it should be noted that, actually no, we'll just look at it more closely now. So here we have the cell, single cell membrane lipid bilayer of the endothelium cells, the vascular endothelium cells, with the endothelin B receptor. And on the other side we have the smooth muscles with separated by extracellular fluid, and this receptor is the endothelin A or endothelin B receptor. And it works through a G protein mechanism, and the target protein is phospholipase C. And as you may know, phospholipase C affects the phosphorinositol 4,5 biphosphate, or PIP2. So what happens is, when endothelin gets secreted by the vascular endothelium cells, it binds to the receptor on the smooth muscles like this, creating a cascade of G protein events. Basically, the phospholipase C phosphorylizes phosphorinositol 4,5 biphosphate, or PIP2, making 2 second messengers, DAG, diacylglycerol, and IP3, inositol triphosphate. So now inositol triphosphate travels to the sacroplasmic reticulum within the cell. Now the sacroplasmic reticulum, when bound with inositol triphosphate, it secretes calcium ions. Now these calcium ions, as you may know from the previous video, calcium ions within the cell causes vasoconstriction, which increases blood pressure. And if the sacroplasmic reticulum is depleted with calcium ions, it stimulates the calcium channels on the membrane, opens it up, so an influx of calcium ions can go in, again making vasoconstriction, increasing blood pressure. So an example of an endothelin antagonist is a drug called bosentan. Bosentan. So what does it do is that it basically blocks the receptor. It basically blocks the receptor. And when it blocks the receptor, it means that it blocks all the events, the G protein events, no inositol triphosphate, and no vasoconstriction, all which decreases blood pressure.